going to do the question 2004 AB number 1. This comes from Form B, and we're specifically looking at question B. The graph of y equals square root of x minus 1 is being cut off at x equals 10 as y goes from 0 to 3. It's going to be rotated around this axis right here, which is y equals 3. And our job right now is to figure out what the radius could be. To demonstrate this, what I'm going to do is I'm going to draw a larger version of what the object should look like. Oops. Actually, let's do this. Let's cross that out. Let's say this is y equals 3. The graph here is x equals 10, and this is the line of rotation. So I'll squiggle that. What you're going to find out is as this gets rotated all the way around like this bottom piece is going to be a solid disk. As this piece gets rotated all the way around, the curve is going to come out like this. So you're going to have kind of a hollow section there. This is why this is the washer. As you go farther out, and we rotate this piece around, you'll find out that the curve goes up like this. We should expect a much larger inner hollow part and a very thin outside part. I will also notice that it was always going to be out this far. So what that's telling me right here, between here and here, is that my outer radius is constantly at all times 3. And it doesn't make a difference how you look at it, it's always 3. On the other hand, my inner radius, which is here and here and here, okay, and technically way out here it's also this piece. This is all inner. These are all r of x. On the other hand, I will notice that no matter what I do here, these values are all f of x. And so what I'm finding out is that r of x plus f of x is going to equal 3. Now if you want to look at it as r of y, well then it'll have to be some function based on y, and that will always have to equal 3. But in this case, f of x is always equal to y, because that's always the height. So therefore, if I'm always looking at my outer radius, it won't make a difference if it's r of x, that will be 3, or r of y, which is 3. My inner radius, let's call this r sub o. My inner radius, r sub I, is going to equal 3 minus f of x, which in this case would be 3 minus the square root of x minus 1. And my inner, that's r of x. And my inner radius based on y will just simply be 3 minus y. Therefore, it says if I'm supposed to find the area, the volume generated around, my integral for the disk washer method, since I'm stacking them this way, which means they're all dependent upon what value of x I'm at, which makes this a dx problem, it's going to be the integral going from 1 to 10. It'll be pi in front. My outer piece would be 3 squared dx. This is my outer. I will subtract the inner, which would be 3 minus radical x minus 1 dx. These are both quantities squared, and therefore, when it's all said and done, I can integrate and say, and put this all together and say it's going to be 3 squared, which is 9, minus 3 minus radical x minus 1 quantity squared dx. If I was going to do a cylindrical shell method, well, I can tell you immediately this has got to be the dy if the disk washer method is dx. So, I'm going to draw out what my shells might look like. And for the first instance, this will be a very tiny shell that's about yay big. Then, my shells all line up on this line right here. My next shell is going to come out about yay far. And it'll look like that. Now it's going to follow this pattern all the way up like this, because the pattern is going to follow all the way down like that. Now remember, this isn't y equals 0, this is y equals 3. The key is, that's my rotation axis. My large cylinder is going to come all the way out to here and fill that in. So, what I realize is that I'm going to look at my cylinders as height. Personally, I always look at height emanating away from the axis, not 10, but from, in this case, the y-axis. Which means, if I do that, this is going to be my outer height. And this curve is going to represent my inner height. Well, again, just like anything else, my outer height, h sub o, is always going to equal, my h sub o is always going to equal the value of 10. My inner height is always going to be, well, let's put it this way. My curve goes yay far. That's going to be an x coordinate. So, I guess I'm going to have to figure out that if y equals the square root of x minus 1, and y squared equals x minus 1, then y squared equals x plus 1 should also be a way to figure out my inner height. So this distance is going to be, oops, I said that wrong. Y squared plus 1 is going to equal x. This will be y squared plus 1. Therefore, I have my outer height, I have my inner height. These are my heights. Since a cylindrical shell uses the surface area, okay, it uses the surface area of a cylindrical shell, which is 2 pi RH. We're also going to need our radius from way yonder up here. In this case, my radius is always coming out like this. Remember, this is my radius right here. Look on top. So if this is my radius here, I'm going to have to use one of these two formulas. In this case, I will use the 3 minus y formula that I figured out from above. So my radius is 3 minus y. There is no outer or inner radius because it just goes straight up or out. That's the one thing about cylindrical shells. There's no outer inner radius. There are outer inner shells, but not outer inner radiuses. Therefore, your integral will be 2 pi times 0 to 3 of, here comes the radius, 3 minus y. Here comes my heights. The first piece is going to be 10. That's my outer. And then I will subtract, so let's put a big bracket around here. Minus y squared plus 1. That's my inner. And lo and behold, dy. That's my final answer. Now you could break this up into two pieces like we did up here, but after a while you should get comfortable understanding how this goes. And so you might even find this just listed as 9 minus y squared. Now, since it is a calculator problem, you're more than welcome to use F and int or whatever features on calculator to solve. If you do, in both cases, you should get 67.5 pi. And there's your answer.